Welcome back, everyone. This is going to be the third lecture of Chapter 30, and we're going to talk about Ampere's law. So the objectives for today are going to be to explain how Ampere's law relates the magnetic field produced by a current to the value of that current. Calculate the magnetic field from a long, straight wire, either thin or thick, by using Ampere's law. So essentially what Ampere's law lets us do, very similar to what Gauss's law let us do, is take a rather complicated equation, look at the symmetry, try to create some symmetry, and then use that symmetry to then calculate the magnetic field at a certain location. Right? Very similar to what we did with Gauss's law, where we calculated the electric field at a specific location. So that's going to be the idea. So let me just kind of get us started here by taking a look at this picture. Let me explain what we're looking at, because it's kind of all over the place. So we have a current-carrying wire that's running out of the page, right? So you see this, the dot at the center. This wire is infinitely long, so it goes infinitely down into the page and infinitely up out of the page. And it creates this magnetic field, and we know we can use the right-hand rule to find the direction of that magnetic field. So you put your thumb in the direction of the current, which is coming out of the page, and then your fingers curl around in the direction of the magnetic field, and you can see that here, right? So it's kind of curls around in this counterclockwise direction. Okay, so what we're going to be doing is creating what's called an amperic surface, or an amperic path rather, or an Ampere path, and it's going to enclose the current, as you can see. So this is just a line. Again, it's not a surface or a three-dimensional shape. It's simply a line in 2D space that encloses a current in the left picture, and then same thing on the right side, but the path doesn't enclose the current on the right picture. Right? So you have path M over here that encloses a current, path N over here that doesn't enclose a current. And we're going to see how I use this to actually figure out, well, what is the magnetic field at some point along this path. Okay, so let's jump over to the next page. So on the next page, we can see that the magnetic field, it's the same picture that I have from the previous page. And I want to do a couple things. So I want to go along this path, and I want to look at that magnetic field as I go along the path. So essentially what that would look like is B dotted with dl, right? I'm multiplying the magnetic field by that length vector, doing the dot product essentially. Now these are both vectors. But if I'm looking at this and I'm talking about, where it kind of intersects the circle, which we know as our magnetic field lines, we know they're going to be circular. Where it intersects that, you're essentially going to have the arc length, right? So instead of writing B dot dl here, I'm going to simply write this as BR d theta, right? Where dl is our arc length, which is equal to r d theta. Okay, so what we're looking at again is the projection of B, the product of B and the projection of dl onto the circle that's passing through, right? So this is the circle that it's passing through. We're just multiplying those two things together. Okay, so let's take this result and combine it with our result from the magnetic field due to a long current-carrying wire that we found in previous lectures by using the Biot-Savart law. So I'm going to now integrate this. So it's going to be the integral of B dot dl, because then we're going to sum up all of those little dl's, right? All, as we go around the actual amperic loop, we're going to sum up all the little dl's, so that's why we're going to take the integral. And this is what's called an enclosed path integral, so that's why there's a little circle inside of the integration symbol. It means it's enclosed, right? So for this to be true, we need to make sure that the loop is an entire loop, right? It's not just a segment of it; it's an actual, entire loop, as you can see in yellow in our two pictures. Okay, so we're going to take this integral, and we're going to replace the magnetic field with our result from the Biot-Savart law. which was mu naught I divided by 2 pi r d theta, because again I'm replacing dl with r d theta. Okay, so most of these terms are going to be constant. Mu naught, the current is constant. The radius here is going to cancel, so it just goes out of the equation, and then we just have the integral of d theta. So this is going to simplify to mu naught I divided by 2 pi times the integral of d theta. Okay, so what is d theta in both of these situations? So for m, for path m, which again is our left path over here, the integral of d theta, well, you're essentially summing up these little d thetas, and you're going to do that all the way around the loop. So of course you're just going to get a sum of 2 pi. Right, so the integral of d theta is simply going to be 2 pi in the case of m. Now for n, it's a little bit different because where we're measuring our theta from, our point over here, is actually outside of this loop. Okay, so if you're adding up all these thetas, you have some negative d thetas over here because you're traveling in this direction. So you're sort of going in that clockwise direction, which is negative. So you're getting some negative d thetas in this direction. Then when you start coming back in this direction, you're going to get some positive d thetas, and then again some negative d thetas here, and you get back to the same position. Well, if you add up all those positive and negatives together, of course you're just going to get a total d theta of 0. Right? You have some positives, some negatives. Really, you're ending up in the same spot. You're not going all the way around the loop. You're just kind of like sweeping back and forth. So our integral, or line integral of d theta here is just going to be 0 for n. Okay, so that brings us to what Ampere's law ends up being equivalent to. Right, so we can essentially take our result here, take our result that d theta is simply just going to be 2 pi in most cases, as long as the current is enclosed in your circle, right, which it is in the case of A, or on the left side of the picture. So Ampere's law comes from this, and it's simply stated as the integral of B dot dl is equal to mu naught times the enclosed current. And this, of course, is one of your equations that's given to you on your equation sheet. So again, I just took that from our result here and the fact that the integral of d theta was going to be 2 pi. I rearranged things a little bit, and this is what we got. Okay. So let's go ahead and move on to the next page and look at, how do I solve a problem like this, right? So we have a strategy. Ampere's law is to calculate the magnetic field created by the current in wires, we're going to use the following steps. First, I want to identify, is there symmetry in these wires? Now, if I go back to the previous picture, there is not much symmetry here, right? This is going to be relatively complicated to solve, right? Because of the way that the path doesn't really have symmetry with our magnetic field, or with our current wires. But we do want to try to find some symmetry. If there is no symmetry, we should just go back and use the Biot-Savart law. Okay, so we also want to determine the direction of the magnetic field created by the wires by the right-hand rule. Right, we can easily do that. We're going to choose a path loop where the magnetic field is either constant or 0. So again, those loops that we picked on the previous page weren't constant or 0 along those loops, but we can choose a loop that is constant or 0. Just for an example, let's say we have a current here coming out of the page. If I'm trying to find the magnetic field at point P over here, I probably want to draw a symmetric circle, right? Just like we did with Gauss's law, right? You want to try to pick a line that's going to be symmetric with your current. And this is going to be the radius, right, the distance away, and that's going to be constant as you go around this loop, right? So that's kind of what we're looking for here. All right, and then we're going to calculate the integral, b dot dl, around the enclosed loop, and then we're going to equate that to mu naught times I enclosed to solve for the magnetic field, right? So we'll do some examples so you kind of see this process in action. Okay. So in slide 9 we have calculating the magnetic field from a current carrying wire using Ampere's law. So I had the picture that I essentially created on the previous slide. I have a current that's coming out of the page. I have now an amperic loop, right? That makes sense because it has symmetry to it. Now they're showing in the picture they're showing the direction of the possible magnetic field, right? They're showing like a radial field and then also a perpendicular field essentially. The radial field here is going to be 0 in all cases because we know that the magnetic field just curls around our current that's coming out of the page. So all of these BRs in the picture are simply going to be 0, and all we really need to figure out are the B thetas as they're labeled. Okay, so we're going to use Ampere's law to solve this. Of course, we're going to start by writing out the law. Now that we have like the vectors drawn, I mean, we can go ahead and draw in maybe what the dl vector is going to be. And we expect the dl vector to be in that direction, which is, by the way, in the same direction as the magnetic field vector, right? They're sort of in the same direction here. Apologize for the bell. Okay, so let's go ahead and then jump over to the to the Ampere's law. So it's going to be the enclosed integral of b dot dl is equal to mu naught times the enclosed current. Okay. Well, this is going to simplify pretty easily because the magnetic field around this loop is constant, right? It's a constant value, so I can pull that out of the integral on the left side. So this is really just what we're calling b theta times the enclosed integral of dl is equal to mu naught I enclosed. Now the integral of dl is just the total path integral around that loop. It's just the length of the loop, which of course is the circumference of a circle. So really this is just b theta times 2 pi r mu naught times I enclosed. Well, what is enclosed in our loop is simply I, right? It's just the current. So that's just going to be I. I can move the everything else to the other side. So our result is the b theta, which is essentially just the total magnetic field, is going to be equal to mu naught I divided by 2 pi r. Now, if you notice, this is the exact same result that we got when we used the Biot-Savart law. It's a good thing that, you know, solving this, we end up taking a whole lot less steps than we did by using when we used the Biot-Savart law, right? Had to use some integration. It took a bit to get here. With the Ampere's law, you can really just go straight to the answer relatively quickly, right? So that's sort of the power of using Ampere's law in an equation like this, question like this. All right, let's jump over to the next page. So the first example was relatively straightforward. We were just looking at one current carrying wire. We were looking at outside the wire. So we know what that result is if we're trying to find the magnetic field outside of any wire. But what if we were trying to find the magnetic field that's inside of a thick wire, right? So this is just another example. You have this cylindrical wire. It has a radius of A, so a capital A is the outer radius. It has a current I naught that's running up through it. And we're trying to find the magnetic field somewhere inside of this thick wire. So what we did was we drew it sort of, looking down the center or down the end of the wire. And we're showing, the radius A. We're showing, the distance from the center to some point that we're trying to find the magnetic field at. And we drew this yellow amperic loop around the center of the wire. All right, so again, if I were to draw in the direction of our magnetic field, well, it's still going to be right, in this direction. Call that dB, and that's also the same direction of dl. Right, so it's still going to be the same direction. We're still going to get a lot of symmetry when we try to solve this. Okay. So we're going to start, now that we have the pictures drawn, we're going to use Ampere's law to solve this. So Ampere's law, again, is the enclosed integral of b dot dl is equal to mu naught I. Because b and dl are in the same direction, this is really just b dl cosine theta, right, because it's a dot product. The angle between them is 0, so b dl cosine theta is just b dl, right? That's why sort of the dot product goes away when we're solving these problems. All right, well, the left side of this ends up being the exact same, right? The magnetic field around our amperic loop is constant. I can pull the magnetic field out. dl is going to be just the circumference of the circle that's created by the loop. So the left side of this just ends up being b times 2 pi r again. The right side is going to be mu naught times this enclosed charge. Right, so we need to figure out what this enclosed charge is. Well, if I think about it, you know, this current is uniformly distributed, right? So that's what would have to be given in the problem. Uniformly distributed through this wire, and it's traveling in this direction, right, throughout the entire wire. So really what I need to figure out is essentially the volume ratio, right? How much of the volume of this, or really I guess technically the area, how much of the area of this cylinder is the current passing through, divided by the total area. And that ratio is going to tell me, you know, how much current is actually going through the enclosed portion of our amperic loop, right? Because we don't care about the current that's outside the loop. All we care about is the current inside the loop. Again, just like Gauss's law. So that ratio that we're really looking for here is going to be the inner area divided by the outer area. Right? And that ratio multiplied by the current will tell us how much of the current is enclosed. Again, I apologize for the bell. Okay, so now I know the enclosed current is really going to be equal to, we'll just say this enclosed current is going to be equal to the ratio, the area ratio multiplied by the total current. If I were to simplify this a little bit, this enclosed current is going to simply be r squared divided by a squared times I naught. Okay, so this gives me enough to go ahead and plug everything back to our original equation. So we know the left side is just going to be b times 2 pi r, and the right side is going to be mu naught times the portion of enclosed current, which is going to be r squared over, oops, sorry, I lost my cursor there a second, over a squared multiplied by I naught. And from here, really, I'm just simplifying and solving, right? So the magnetic field is going to be mu naught I naught divided by 2 pi times r divided by a squared, right? One of the r's canceled out from the left side, so I just have r left on the right side. And this is for when r is going to be less than or equal to a, right? So when you're inside this thick wire. Just combining that with the solution from the previous problem, if we're looking for something outside of the wire, it's simply going to be our previous result, which is mu naught I naught divided by 2 pi r, where r is greater than a. Right, so you have these two solutions here, one for when you're inside the wire, one for when you're outside the wire. Okay. Let's jump over to the next page. So this is just a graph of our result, right? So I can take those equations that we have. A squared was a constant, right? So if I'm taking a look at this, this is going to be our maximum value for the magnetic field. It's going to start at 0 at the center. It's going to linearly increase because our equation was a function of r, right? So it's going to literally increase like that. And then when I get to the outer edge, which is our A, we'll start to decrease as I get further and further away from this wire. And that's going to be a function of 1 over r, as we see from the previous equation. Okay, so one last thing. What if we had, multiple wires? How do I deal with that? And how can I use Ampere's law to help me? So this picture is just, there could be arbitrary paths. We're not really concerned about finding the exact magnetic field, but you can still use Ampere's law to help you get some information. The point here that we're trying to make is you need to relate it to the currents that are going through the loop, and the direction of the currents do matter, right? So for instance, let's just take a look at picture A. You have multiple currents that are inside my amperic loop here, right? You have 2 that's going down, 5 going down, 3 going up, and 4 going up. So the enclosed, let's say just write out Ampere's law again real quick, which is going to be equal to mu naught times I enclosed. Well, again, the left side is always going to be B 2 pi r with some symmetry, but even so, to find the enclosed charge is really going to be the key here. So the enclosed charge, we need to be a little bit careful with the direction. So let's just say that going down into the loop is going to be negative, so I have a -7 here, and then coming out of the loop is going to be positive. Right, so my enclosed charge here in this example is simply going to be 0. Okay. The next example, notice how my amperic loop is only enclosing one of them, right? So here my enclosed charge is just going to be 2. In the last example, I have 7 in here, I have 5 into the loop, and then I have 3 coming sort of out of the loop. So I have 12. Let's say it's -12, then I have a +3, so the total here would be 9, right? 9 amps for the enclosed charge. All right, so if you see a problem like this, that's kind of how you kind of want to walk yourself through it. What is the enclosed charge? That's all that matters when you're looking at Ampere's law, and go from there. All right, well, so we're coming up to the end of this lecture. See you guys next time.